Okay, so let us discuss a very important SFR, which is the program status word. We will be looking into the details of the program status word. So let's start. This is a SFR, special function register. Okay, and the program status word is a 8-bit register. Let me draw it here. So each of the bit has got a meaning. So the most significant bit is your CY. This is your carry bit. Okay, then we have the auxiliary carry. Then we have another bit called F0. This is your auxiliary carry. Auxiliary carry. Then this is available for the user to be used during the program. Then this is your RS1 and RS0. So RS1 and RS0, RS1 and RS0, they could be 00 or 01 or 10 or 11. This is basically used for bank selection. Bank selection. So we know that there are 4 banks in 8051. If you are writing 00 in RS1, RS0, then bank 0 is selected. If 01 is written, then bank 1 is selected. If 10 is written, then bank 2 is selected. And 11 is written, then bank 3 is selected. Then next bit is quite important, overflow bit. We'll discuss about it in detail. Then we have the don't care bit, and then the parity bit. So let us take one by one and discuss them in detail. Okay, so let's start with the uh, carry flag. So carry flag is set whenever there is a carry out from the D7 bit. Okay, so the accumulator, it is having 8 bits from D0 to D7. If there is a carry on D7 bit because of some operation, normally because of addition or subtraction or uh, multiplication, any operation results in a carry at D7, then this bit is set. Okay, other way to set this bit is using the bit instruction, like your set B C. So C is carry, and set B instruction makes the value of the carry bit equal to 1. Similarly, the carry bit can also be made equal to 0 by using CLR bit. CLR instruction, sorry. CLR C will clear the carry bit. Okay. Then come to the auxiliary carry. Auxiliary carry, uh, let's see auxiliary. So we have this accumulator. It has got 8 bits. Okay. The lower 4 bits and the upper 4 bits. This is your D0, D1, then D2, D3, D4, D5, D6 and D7. This is the most significant bit. So whenever there is a carry from the D3 bit to D4 bit, okay, during any operation like the add operation or the subtract operation, if there is a carry from D3 to D4, then the auxiliary carry flag is set. We will look into it with the help of an example. Okay, then uh, let me discuss first of all them, then I will take example to illustrate how they work. Come to this parity flag. uh, this basically tells about the number of ones in the accumulator. If number of ones in the accumulator is odd, if it is odd number of ones, okay, then P is equal to 1. and if it is even, then it is equal to 0. So this is your parity flag. I will talk about this overflow flag after some time when I have discussed the signed operation. Okay, so let me take some example to illustrate the operation of the PSW register. Okay, so let me take an example. Move a comma hash 56h. That means I am saving 56 in A. Let me take another instruction. Add a comma hash 95h. So 56h is in binary. If I write it down, 0101 and 0110, and 95h is equal to 1001, then 0101. So basically, after this instruction, these two numbers have to be added, and this is stored in A. Okay, so 01 is 1, 10 is 1, 11 is 0, and 1 is carried here. Then 10 is again 1, 11 is 0, 1 is carried here, so it becomes 1, 10 is 1, and 1. Okay, so you could see here there is no cy will be equal to 0. Why? Because there is no carry beyond d7. No carry beyond d7. So cy is 0. So if these two additions of this number, if would have resulted in 10 or 11, then there would have been a carry and this would have been set. But in this case, it is not. Okay. What about the auxiliary carry AC? So d3 bit is this d3 bit. Okay. So if these two are added, then basically there is no carry transferred to d4. Okay, so AC is also equal to 0. What about parity? So number of ones are 1, 2, 3, 4, 5, and 6 ones are there. So P is equal to again 0, because number of ones, if they are even, then P is set to 0. Otherwise it is set to 1. Let me take one more example wherein these flags are affected. So I'm writing move a comma hash 9ch, then add a comma hash 64h. Let me write down the value in binary, then 1100, then 64 is 0110, and 0100. If I add these two numbers, 0 here, 0, 1 and 1 is 0, 1 is carried here, 1 plus 1 is again 0 here, 1 is carried, 1 plus 1 again 0, 1 is carried here, 1 plus 1 again 0, 1 is carried here, 1 plus 1 again 0, 1 is carried here, 1 plus 1 is 1 0 1 0. So 0 I've written here, 1 is carried, so carry flag is set. And one more thing, there is carry from d3 to d4. Just see here, this one. So auxiliary carry will also be set to 1. What about the parity? Since there are no one in the accumulator in the final result, so parity will be equal to 0. Okay, so this is an example to illustrate how AC and CY flag and the parity flag gets affected during the course of operation of add instruction. Okay, so before going into the overflow, let us see the concept of signed numbers. It is very important. Okay, so basically to understand this, we know that numbers are either positive or negative. Okay, but the microcontroller do not understand this positive and this negative sign. Okay, so we have to give the information in terms of 1 and 0 to make the processor understand that whether a number is positive or negative. So what is done, so we have 8-bit register where we can store the numbers. Okay, so what is done, the most significant bit, the D7 bit, is reserved for sign, sign, sign. If it is sign is, if it is 0, then it is considered to be a positive number. If it is 1, then the number is considered to be negative. So that means the maximum number, a signed maximum signed number that can be represented in 8 bits is how much? So it goes from 0, so when all are 0, till 127, 127, it becomes 127 when this is 0, and rest of them 1 2 3 4 5 6 7, so this becomes 127. So these are your positive numbers, because 1 2 3 4 5 6 7. Why? Because sorry, wait, okay, okay, sorry for that. So you could see here that the first bit, or the most significant bit, in all the cases from 0 to 127 will be 0, so all the numbers are positive numbers. Then when it turns, if I add 1 to it, so it becomes 1, and then 7 zeros, 1 2 3 4 5 6 7, 7 zeros are there. So how much it is? So if it is an unsigned number, it would have been 128, but this is signed number, so this basically refers to the sign. Now this number is a negative number, and what is its value? Its value is minus 128. Okay, then the next number would be 1 2 3 4 5 6 1. Okay, so minus 127, and so on till we get minus 1, and minus 1 would be basically be all ones, 3 4 5 6 7 8, all ones. This would refer to the number minus 1. Okay, and 0 will be basically be all zeros, so 0 is neither positive or nor negative. Okay, so this is the basic concept of signed numbers. Okay, so these are the negative numbers. Fine. So how you have to understand this, how the negative number is stored in microcontroller. So this is how it is stored. Okay, so we will see some operations to understand the how signed numbers are added and how it is subtracted. Okay, and how the overflow flag is affected. So basically our intention is to understand how overflow flag is affected. So whenever there is a carry from D6 to D7, there is a carry from D6 to D7. Okay, D6 to D7, but no carry out of D7. That means Cy is equal to 0. Okay, this and this condition, if they are met, there is a carry here, and Cy is 0, then overflow flag is set. So first condition. The second condition is that there is a carry from D7. So D7 there is a carry. Okay, but Cy that means Cy equals to 1, but there is no carry from D6 to D7. So there is no carry. Okay, so in this case also overflow will be 1. These are the two conditions wherein the overflow flag will be set. So basically the overflow flag gives you the information if there is any error in